Okay, we're going to do a video on two of the important practicals in the A-level chemistry, AS-level chemistry specification. This one in particular, the first one we're going to look at, is particularly important, and when it comes up on an exam paper it can be worth a considerable number of marks. It can come up in a variety of guises. So the one on your syllabus is to prepare a pure dry liquid, and the one on the syllabus is of 1-bromobutane, but that can be really any pure dry liquid that the examiner decides to ask you about. The important thing that you need to understand is that the method which you learn here or in your notes or in your textbook is the same method, but it is applied to maybe different reactants and obviously different products. You have to sort of apply that and think on your feet in an exam situation. But the key thing is, it's when you're making a pure dry liquid. The other one is a reaction where we follow the rate of hydrolysis to show the relative bond strengths of carbon-halogen bond in organic molecules. So what we're looking at there is the carbon-chlorine bond versus the carbon-bromine bond versus the carbon-iodine bond in a variety of organic molecules. And how do we monitor the strength of this bond practically? In other words, visually, by reacting these with something and actually making an observation which tells us this bond is stronger than this one, which is stronger than this one, or weaker. Okay, so we'll have a look at that second. That's another important practical in this haloalkanes topic. So we'll start first. We'll go into the preparation. First of all, this is quite a lengthy practical. If you remember from class, it took us quite a while to do, and at the end of the day we probably got about 2 cubic centimeters of product at the most. Okay, so we'll start right at the very start, and the first thing that you do in this is you take your little pear-shaped flask, and that's a pear-shaped flask there for those of you who cannot remember it. The reason why we use it is because it allows heat to spread quite easily, whereas a beaker with a very flat bottom, okay, you get a lot of concentration of heat around that base. This allows an even distribution of heat, which is what you want in this reaction, because hot spots in this reaction can give you actually undesired products. So you take that and you put into it a few anti-bump granules, which are little solid inert substances which provide a nice smooth boiling. If you think about a kettle, if you leave it to boil, it can get quite plumpy, and that'll be dangerous in this environment. So we put in something which gives a nice smooth steady boiling, and those are called anti-bump granules to prevent that bumping action you might find in a kettle. So in that pear-shaped flask that we have there now, as well as our anti-bump granules, we put in there some sodium bromide, and we put in there some about 50% concentrated sulfuric acid. And the reason why we do that is because we're carrying out the reaction. We're starting off with an alcohol. In this case, the alcohol that you begin with would be butan-1-ol, and we're trying to eventually convert that butan-1-ol into 1-bromobutane. Okay, and that's the reaction that we're looking for. But if you see here, we don't start off by adding hydrogen bromide to it. Okay, hydrogen bromides are fairly unstable. We don't have bottles of it sitting around in the lab. So what we've got to do is we've got to actually make our hydrogen bromide, and this is a bit new for A level, what we call in situ, which means in the place of the reaction. And we carry out we add these to the flask to begin with, and that actually makes our hydrogen bromide. So if we look at the equation now, lots of people will be tempted to write this equation here, and can I just make you aware that is wrong and will cost you marks. You do not get sodium sulfate, you get sodium hydrogen sulfate. Okay, in this instance, and if you look there, we have now made our hydrogen bromide in a place of our reaction. Okay, and our butan-1-ol will be in there with the sodium bromide and with the sulfuric acid, and this reaction will then take place. Now, it's not quite as simple as that in terms of what we would have did at GCSE, was you just added these things together and we got product. There's a little bit more to it in this case. Okay, now, when I have my pear-shaped flask, I need to obviously add all of this, but there's a problem here in that whenever we add the conc sulfuric acid, this reaction can get extremely exothermic. Now, if you remember from GCSE and even earlier in A level, when it gets very exothermic, conch sulfuric acid can act as a dehydrating agent. And dehydration means to remove the elements of water, so oxygen and hydrogen. So this can turn into a variety of things. It might turn into carbon, it might turn into water, it might turn into an alkane such as butane, okay, through dehydration. But the key thing is, you're not, if this happens and this conch sulfuric acid reacts in here and the reaction gets extremely hot, you will not get your desired product, and lots of your reactant will be turned into these particular things here. That means that your yield of desired product plummets. Now, how do we get over that? Well, we've got to add the conch sulfuric acid really very, very slowly. And not only do we add it slowly, but we also add it with cooling. And what that means very simply is we maybe add it through this piece of apparatus here. So if I'll just talk you through this very quickly. We have a dropping funnel here, and I just have an example of a dropping funnel just there. Okay, so you have this tap here which you can allow your substance which is in the funnel to drop into your reaction vessel nice and slowly. The tap's very easily controlled and you can add it drop by drop. Okay, you might have a diagram of it in your notes, something like this, but it gives you a nice controlled flow of your reactant, and in there you will put your conch sulfuric acid. Okay, and down here you'll have your sodium bromide, your butan 1-ol, okay, and you'll have some water as well, and we'll ignore that heat for the minute. Okay, and you will add the conch sulfuric acid, and you usually do this also in an ice bath, so with water and a few cubes of ice in it, to keep everything nice and cool. And that prevents these side reactions that we spoke about here. The other side reaction that can also happen, if you remember your group 7 chemistry, is that when conch sulfuric acid reacts with bromide ions, which are in sodium bromide, that also takes those bromide ions and turns them into bromine. Okay, and that is an oxidation reaction. Okay, where this goes from -1 to 0 oxidation state, and it has lost 2 electrons. And again, if the conch sulfuric acid gets hot, or the reaction mixture gets hot, and the bromide ions are in there, that's another thing that can happen. And that will also, instead of turning your bromide ions into hydrogen bromide, you will also get further side reactions, and that will bring your yield down further. And when you were doing this, lots of you probably would have noticed inside your round Persia flask, a brown colour. And that brown colour is because of the formation of a little bit of this bromine. It's pretty much unavoidable, but the reason why we carry the reaction out by adding the sulfuric acid drop-wise, and we do it in a cold environment, is to minimise those side reactions and therefore get as much of our eventual product as is possible. So we've done that. We've got everything in here, and we've done it in a nice and cold and controlled environment. We've tried to avoid getting side products, and we've tried to avoid getting bromine. Okay. Our next step then is we've got to take this reaction. We've got to heat it for a long time, because the activation energy is high in this reaction. The bonds and the reactants are very strong. But there is a problem. If we did this in a beaker, as we might have done at GCSE, the reactants and the products in here both have got very low, relatively low boiling points, and if I did it in a beaker and I heated it in the beaker, they would simply evaporate out and fill the room with very noxious and horrible smelling gases. So how do we get over that? Well, hopefully you know that we have met this process already, and it is a process called reflux. So what we do is we take this is a pear-shaped flask, but if you just or a round bottom flask, if you just imagine that that's our pear-shaped flask at the bottom here, and we have all of our reactants in here now. We've added them, very controlled, and we've got to heat them to break the bonds and reach the activation energy. So what we do is we carry out heating under reflux, and we take our flask and we fix to it this time a condenser. So we take what's called a Liebig condenser, and you need to know that term. We pop it onto our flask, okay, and that allows us to heat the bottom of the flask and everything to rise up, and we have water going in at the bottom, okay, and if you can just see maybe this tube that runs up the middle surrounded by a water jacket, and we have water coming out here at the top, and that's important when you're labeling these in an exam, that you do exactly that. The water goes in at the bottom and out at the top. If you think about it, that means that as gravity pulls against the water, the entire water jacket is completely filled with water. If you did it the other way around, you run the risk of getting some air bubbles in here. So we do that, and that gives a nice cold water jacket around the reaction, the tube, okay, and the inside of the condenser. Now when we heat down here, everything will get very hot, it'll start to boil, and it will rise up as a vapour would do, and it'll hit the nice cold inside of this water jacket, and it will condense and it will return, and it will continue to that continual evaporation and condensing, which is heating under reflux, okay, for as long as you want, really. And what it does is it prevents any loss. So this is just open here, as you can see. It prevents any loss of anything that's volatile, reactants or products, escaping out into the room, and it means you can keep these things at extremely high temperatures for a very long period of time, breaking all the bonds and getting hopefully as much yield as is possible. Okay, so that's heat under reflux, and that would be your next step. And at the end of that, you will have in there, you'll have what we call a crude product. So if I go back to here, my 1-bromobutane will have reacted with some of my HBr, and I will have some of my 1-butan-1-ol will have reacted with HBr, and I will have this. Now, I will also have left over some unreacted sulfuric acid. I will have some water in there. I will still have some unreacted alcohol. But if you remember at the start of this, we said how to make a pure and dry liquid. So that's exactly what we've got to do. We've now got to get rid of all of these unreacted reactants or unwanted products, and this is what we're going to have a look at now. Right, so we've got ourselves refluxed. Then what we've got to do is try and get the product out in some sort of purity. So what we'll do is we'll take our little flask, okay, which we have here, and we will change the system. We'll put in what we call here, this is called a still head, and we'll now bung it, and we will heat it here. And what that will do is, again, okay, so we'll get that sort of a setup. I haven't got a still head here, but you get the picture. We'll put something in there which forces any vapours up and across. Okay, and we're now into distillation, and what we will do is our product, okay, and some other things as well also, will rise up, go across, and we can collect them over here. And we usually collect about a third roughly of what was in here. Now that will still have some of these in them, but to a much lower extent. So we've still got a bit of that, we've still got a bit of that, we've still got a bit of that, but we have increased the concentration, as distillation does, of our desired product. Okay, and that will be in this flask here. And we've now got to take this slightly purified product and start to purify it even further. Okay, so the first thing that we do is we will take our product and we will just simply transfer it this time into one of these. Okay, so back into a tap funnel or a separating funnel, something like that, if you're just about to see that. Okay, and we will give it a really, really good shake up with some water. Now, why do we use the water at that point? Well, the water will allow anything that is water soluble to dissolve out. And the key thing is that this is not water soluble. It is not miscible with water and will stay separate. So this, the sulfuric acid that's unreacted, the unreacted alcohol, and of course the water itself, would make its way into here, and we shake it up, and we have two layers. One layer will be an aqueous layer, and one layer will be our organic layer, the layer that we actually want. Now, how do we decide which layer to keep? A frequent exam question. Well, we have a look at the densities, okay, and you decide the aqueous layer will have a density of 1 gram per cubic centimetre, and if you find out the density of your organic layer, let's say it's 0.79 grams per cubic centimetre, then the organic layer would be on the top, of course, and the aqueous layer would be in the bottom. The actual density of the 1-bromobutane is 1.27 grams per cubic centimetre. So in actual fact, in this instance, your organic layer will be on the bottom and your aqueous layer would be on the top. And then you simply run this through and you collect your desired layer, the lower one. Always take the stopper out, by the way, before you do this, otherwise it will just simply suck air in from the bottom and mix everything back up again, and you won't get a good separation at all. So, and you keep that layer. Now you might think, oh, that's got to be a pure layer by this stage. Well, it's purer, but you still have a variety of things in here in sort of trace amounts, very, very small amounts, that you want to get rid of. Okay, so we've got to then again see how do we actually get rid of these. Well, we do the same again. We return this 1-bromobutane back into a separating funnel again, but this time we give it a good mix up, a good shake up with some sodium carbonate solution, and we'll have a look at what the reason for that is. It's because we still have some unreacted acid in there, which just trace elements which we simply need to get rid of, and that gives us carbon dioxide and it gives us water. So we've got rid of our hydrogen ions from our acid, but we've produced some water and we've produced some gaseous carbon dioxide. Now we need to be careful with that, okay, because this is a sealed environment and we've got carbon dioxide. So how do we deal with that? Well, after we've given it a really good shake up, what we do is we do not let the carbon dioxide out by opening the stopper, because the stopper might fly out. This is a very wide opened mouth here, and liquid might pop out in the same way as you open a shook up bottle of Diet Coke or similar. Fizz may well bring some of that liquid out. We don't want that. So what you've got to do, and you've got to make it clear to the examiner, is you shake this up, you invert it, okay, so turn it sort of upside down, and you slowly open the tap here, and that will let the carbon dioxide out in a very, very controlled manner. So you shake, you invert, you open the tap, and you let the carbon dioxide out. So that's that done, but now we've got still a little bit of water mixed in with our 1-bromobutane, our desired product. So our last step to get rid of the water is we run this crude or fairly pure 1-bromobutane now at this point, or whatever it is. It may not necessarily be 1-bromobutane, depends what the examiner asks you about, but as I said earlier, the method is still the same. And what we do then is we will put it into a little beaker. We will add a few granules, not many, okay, of a drying agent. Now the one that I would frequently use is anhydrous calcium chloride, and if you're asked to name a drying agent, you must mention the word anhydrous. Okay, other ones are things like magnesium sulfate, sodium sulfate, okay, but anhydrous calcium chloride is the one that we use, and we just put that in and we give it a bit of a stir up, okay, until the whole mixture goes nice and clear. And at that point, the anhydrous calcium chloride acts a bit like a sponge and has absorbed the last few molecules of water, and now you have a fairly pure C4H9Br on your hands. Okay, so we've got to get a nice pure product of this out again. So how do we get our last little bit of C4H9, 1-bromobutane, or whatever it is? Well, in this instance, we will now what we call re-distill. Okay, so we distill for a second time basically, but we will collect the product at the actual boiling point of I'll just write of our desired product. Now that would be plus or minus about 2 degrees, plus or minus 2 degrees of the boiling point of your desired product, whether that be 1-bromobutane or something else. Now, they will frequently give you this information at the start of the question, so please look out for it. Okay, and then at the end of that, you should have a fairly pure product, which if you were a organic chemist, you might be able to put on the market and sell to someone. So that's how we get a pure dry liquid, okay, starting with certain reactants. Okay, in this case it was butane, 1-all sodium bromide and 50% sulfuric acid, but that will depend on what the examiner asks you. But the method, the principle behind it is exactly the same. Okay, we're going to look at the second practical then, which is how do we follow the rate of hydrolysis, okay, to illustrate the strength of a carbon-halogen bond. So we're going to look at carbon-chlorine versus carbon-bromine bond. And we'll look at, let's say, 1-bromo-butane versus 1-chlorobutane. Now, how do we actually follow this and gain observations from an experiment to see which of these two bonds is the strongest or the weakest? Well, we really do it by putting them under exactly the same conditions and seeing which one breaks most rapidly. Now, obviously, we can't see which one breaks most rapidly with our eyes, so we've got to get this bond broken, and we've got to be able to attain some evidence, some chemical evidence through observations that the bond has indeed actually been broken. So what we do is, and I'll take it for sort of a general halogen, is we react it with water. Okay, and we do that at about 60 degrees Celsius, and we do that also dissolved in a little bit of ethanol, okay, because haloalkanes do not dissolve very well in water, so we use ethanol to try and to get the water and the haloalkane to mix readily together. So you must mention the fact that you have a little bit of ethanol in there as well, act as a solvent. And what happens then when we do that is exactly as I said earlier, hydrolysis. And hydrolysis means the splitting of water. So you can see the water has, the OH has gone to there, and the H from the water has joined with the halogen to form a hydrogen halide. Now this is important. We know that hydrogen chloride, hydrogen bromide, etc. in water are strong acids, so they dissociate into the halide ion and the hydrogen ion, and we use that piece of chemistry to actually follow the rate of this reaction. Now, if I do all of this, and I also put in here a little bit of silver nitrate and its solution, and you must make it clear to the examiner that you understand it is solution, because actually this can be your source of water, the aqueous in the silver nitrate. We know from, hopefully, from GCSE that silver ions in silver nitrate will react with halide ions, and as soon as they react they form a silver halide. Now we know that silver halides are insoluble in water, and if it was a silver chloride we would see a white precipitate. If it was a silver bromide we would see a cream precipitate, and if it was silver iodide we will see a yellow precipitate. Now, how do we use all of this chemistry to decide which of these bonds are the weakest or the strongest? Well, in this reaction here, what we're doing is we're breaking that bond. You can see that hopefully. Okay, and we have got silver nitrate in here, which will, as soon as the halide ion is free, can react with it and form a precipitate. So in other words, the quicker this precipitate is formed, the quicker this bond has broken. And therefore the less energy, if everything is in the same environment for the same time at the same heat, then the less energy it has needed to break this carbon-halogen bond. So for example, if the yellow precipitate formed quickest, okay, so if we set the experiment up, but 3 test tubes, okay, all at about 60 degrees. We need a little bit of heat to help get the reaction going. Okay, so all our test tubes have got in them our C4H9X, so our 1-bromo-butane, 1-chlorobutane, 1-iodobutane, etc. And silver nitrate also, aqueous, that's important because that is our water. Okay, and we would note how quickly the precipitate forms. So the quicker the precipitate form, the quicker the bond is broken, and therefore the less energy it has taken to break that bond, and the weaker the bond enthalpy actually happens to be. Okay, so those are two reactions that you've got to be aware of, two practicals. The first one is a major one, the second one not so big, but still one that causes students a little bit of problems. You'll notice here sometimes actually they also ask you to write two equations, so those are the equations that you would have to be aware of. Obviously you would replace my X here with chlorine or bromine, and my alkyl group here with C4H9 or whatever it happened to be in the question. Okay, and then that's the second one again. This X will be replaced by chloride or bromide or whatever it was in your original haloalkane. So hopefully that's of some use to you guys. Two important practicals. First one especially important and can be worth a lot of marks if it crops up, and the second one again is one that sometimes causes a little bit of difficulty because of the sequence of events that's occurring there. Okay.